I'm going to talk to you about conservative forces and introduce a concept called potential energy. So conservative forces have this specific characteristic. I'm going to show you what I mean. It has to do with work. Okay, so let's talk about gravity, force of gravity. I've got a ball here, and I just lower the ball 2 meters, and then I raise it 1 meter, then I lower it 5 meters, and then I raise it 6 meters. Okay, and let's look at the work done by gravity while I was doing all this moving the ball around. Okay, so if I look at this first, it has a mass of 0.5 kilograms. If I move it down 2 meters, the force of gravity is 5, delta y is 2, the angle in between is 0, so you end up with 5 times 2 times cosine of 0 is 10 joules. So the work here is positive 10 joules done by gravity. Okay, I am holding it as it goes down. So I'm doing this. That's all I'm doing. I'm applying an upward force. Okay, so there's 10 joules. 10 joules work done by gravity. Now, if I find the work for this, it's going to be 5 times 1 times the cosine of 180. So work done by gravity is negative 5 joules. Okay, then I do this one. 5 times 5 times cosine of 0, 25 joules. Looks like a 35, but it's a 25 joules. Okay, positive, because they were in the same direction. And then I lift it up 6 meters. 5 times 6 times cosine of 180, negative 30 joules. Okay, why did I bother doing all that? Because look at this. 10 plus negative 5, that's 5, plus 25, which is 30, minus 30, the total work done by gravity over the whole trip is 0 joules. This is what a conservative force does, is if you return it to its original position on that whole round trip, the work done by that force is 0. So gravity is a conservative force. Anytime I take this thing right here and I do, if I wind up at that same spot, I've done, not me, I've done some work, but gravity has done a total of 0 joules of work. So conservative force, same location, same position, 0 total work done. Okay. As a contrast, let's look at non-conservative force. Okay. If I apply a force here, this is actually kind of 2 different forces. So let's talk about friction. I apply a force on a box and I move it delta x. Friction is pushing in the other direction. Okay. And so the amount of work this does is force of friction times delta x times cosine of 180, the angle between, so times negative 1. Well, then I take that box and I push it back in the other direction. So it's back at its original location. Well, on this trip, friction was in that direction, delta x is in that direction, and so I get another negative f delta x times f times delta x, sorry. So you can see if I add those together, I get a bigger negative number. So when I got back here, friction did negative work. It did some amount, some number of joules of negative work. I got back to the same location, but there was definitely not 0 work done by that force, by the force of friction. Okay. Why this is important is because this tells me that the work done by gravity has to do with the relative location of the object. And this allows us, when we have conservative forces, we can represent them as kind of placeholders in the energy world. We don't have to do the work done by gravity every time we do a problem where things are going up and down.